Some covalently bonded molecules have multiple bonds holding parts of them together. When we go to draw a Lewis structure, we need to represent those double and triple bonds appropriately. And throughout this lesson, I'm going to show you how to deal with molecules that have multiple bonds. Let's go. On all my lessons with drawing Lewis structures, I start with this screen. I'm not going to go over it, but you can pause and write these down if you haven't yet done so. If you already have these written down, well then let's find out what this multiple bonds thing is all about. And as I mentioned, sometimes atoms may share more than 2 electrons, and each bond line represents 2 shared electrons in a covalent bond. So a double bond is sharing 4 electrons. A triple bond, like the one you see down at the bottom, that's sharing 6 electrons. We'll never have a quadruple bond. There'll never be 4. So we either have single bonds, we have double bonds, or we have triple bonds. While you're learning this, one really good question is, how are you going to know if a molecule has multiple bonds? If I'm trying to draw this Lewis structure, how am I going to know that I need to include multiple bonds in it? Well, you won't. But if you follow all those steps that I had just a bit ago, and you've written them down, once you follow those steps, you will get to the right answer. The best way to learn is to do a practice problem. We're going to start with carbon dioxide. Now, you have no idea if carbon dioxide has multiple bonds in it or not, except I gave you a hint up here, right? But you wouldn't need to know. If you follow the steps, you'll get to the right answer. Let me show you how. Add up our valence electrons. We have carbon, 1 carbon right here, oxygen, 2 of those. So what we need to do is figure out how many valence electrons we have total. Let's find carbon on our periodic table. It's right here. It is in group 1, 2, I'm going to jump, 3, 4, which means it has 4 valence electrons. Times 1 carbon equals 4 valence electrons going to show up to our party from the 1 carbon. Each oxygen, let's find oxygen right here, is going to bring 1, 2, 3, 4, 5, 6 because it's in group 6A, 6 valence electrons, but 2 of them are going to show up in our molecule, so 6 times 2 is 12. I just add these up. 4 plus 12 is 16, and E negative is shorthand for electrons. I'm just keeping track for myself so I know what these numbers refer to. I have 16 electrons to build my structure. Add or subtract a formal charge. There is no plus or minus up here, which means this CO2 does not have a formal charge. We build the skeleton structure. Well, what's going to go in the middle of our skeleton structure? We have carbon and we have oxygen. I can look up their electronegativities, but their position on the periodic table will tell me. As I move this direction, they become more greedy, right? This way and this way. So oxygen has higher electronegativity than carbon, which means carbon's going to be in the middle. Let me give you a little hint. If there's carbon present, it's probably going to be the middle because carbon is kind of a special thing. It can make 4 covalent bonds, though a lot of our structures have carbon at the center or lots of carbons at the center if we get into organic chemistry. I'm going to attach 2 oxygens. Now here's the thing. I don't know where those should go. I mean, I do, but if I was you, you wouldn't know where they go. So let me erase them and say, well, why would I what if I put them like this? Would that be okay? Yeah, in my class, for right now, it'd be totally fine to do that. I just tend to draw these where everything is trying to get as far away from each other as possible because, well, that's what tends to happen with electrons. They're all negatively charged, so they're trying to get away from it. I'll put the oxygens over here. Remember, the line represents a covalent bond where they're sharing 2 electrons. That carbon is sharing 2 electrons with this oxygen. Now, let's add electrons around the outside of the molecule. I have to use all of them that we calculated right here. So we have 16 electrons to put on here. I always start on the outside edges around here and never start on the center. You're going to see why when we start to do this multiple bonding. I've used 2, 4 electrons, 5, 6, 7, 8, 9, 10. I'm going to come over here and start to fill this up. 11, 12, 13, 14, 15, 16. There we go. I've used up all 16 electrons from step 1. Add brackets and the charge if it has a formal charge. It does not. Draw resonance structures. We haven't learned that yet. If you want to jump to that lesson, there's a link down in the description and you can jump to that one. So this does not have resonance. I'll just tell you that. And then we check our answer. Now, hopefully some of you are like, wait, you screwed up, guy, because this oxygen has 2, 4, 6, 8 electrons around it, and so does this oxygen, but this carbon is not okay. It only has 2, 4 electrons. Oh, geez, let me get rid of that. It only has 4 electrons around it. It has to have 8 when we're done. Well, I've already used 16 electrons. Right here it says we have to use all of them from step 1, but we can't just bring more electrons in and start putting them anywhere we want. So here's what we do. I say that this is what I use with my students. I say that this carbon is unhappy and I've run out of electrons. When I run out of electrons and I have an unhappy central atom, the easiest thing to do is that sharing is caring. So I'm going to tell this oxygen, you need to share 2 more of your electrons with that carbon. Oxygen's fine with it. It doesn't care because it still has 2, 4, 6, 8 electrons around it. This oxygen's fine. It still has 8. This carbon now has 2, 4, 6. Ooh. So we're not quite there. And I can't invent more electrons, but that's okay. If you think about this, we go back to our rule. We have an unhappy central atom and we've run out of electrons. Well, sharing is caring. Now, it doesn't matter which electrons I come over here and force this oxygen to share at this point. I'm just getting rid of 2 of them and showing that they're going to be shared now. So this is kind of a rough Lewis structure, but that's totally okay for our purposes while we're learning this. Now let's see if it fits all the rules. Carbon has 2, 4, 6, 8. It's okay. Oxygen right here, 2, 4, 6, 8. This oxygen, 2, 4, 6, 8. Well, this must be carbon dioxide. It has a carbon with 2 double bonds going over to the oxygen. Next one, carbon monoxide. Notice this is similar to the last one. I put carbon dioxide up there and there were 2 oxygens. This is monoxide. Mono means 1. But nothing changes about our rules. We don't know if this has multiple bonds or not, and it doesn't even matter. All we need to do is follow the steps. We have 1 carbon and 1 oxygen. Each carbon, let's come over here and find it, brings 4 electrons to our party. One carbon's going to show up. That's a total of 4 electrons. Each oxygen, we already looked it up before, brings 6 electrons. 1 is going to show up to the party. That's a total of 6 electrons. We add these up. 4 plus 6 is 10. Does it have a formal charge? No. So we're done with number 1. Number 2, build the skeleton structure. Well, which one's going to go in the middle? There's only 2 of them, so we're not really concerned about a middle. I'll just place them next to each other and then show that they're bonded together. Step 3, add all of our electrons around the outside. So far, we've only used 2 because we have 1 bond in there. I'll just go ahead and start putting them around the oxygen because that seems like a good place to start. So I've used 2, trying to get to 10, 3, 4, 5, 6, 7, 8, 9, 10. Okay, well, that's fine. I can't invent more electrons. It just is what it is. So I added electrons around the outside of the molecule. There is no formal charge. So I'm going to kind of pause here because hopefully you're recognizing we've got a problem. Carbon does not have enough electrons. It needs to have 8. Oxygen is fine, but carbon isn't. Can't invent more electrons. What do? Well, we have an unhappy atom. We've run out of electrons. Sharing is caring. So I'm just going to take my eraser here and remove 2 of these. It doesn't matter which ones. And show that now they're being shared. I'm going to clean this up a little bit because I already know what's going to have to happen and I want this to look nice for you. And you should be saying to yourself right now, wait a minute. This carbon still does not have 8 electrons around it. Oxygen does, but carbon does not. Same rule applies. We have an unhappy atom and it needs more electrons. We can't just invent them, but we can say, hey, what have you shared? Well, look what we've just done. We've made a triple bond between the carbon and the oxygen. They're sharing 2, 4, 6 electrons. And they each have a lone pair on the outside. That's still a total of 10 electrons. It does not have a formal charge. It does not have resonance structures. And we just checked our answer. So carbon monoxide is held together by a triple bond between carbon and oxygen. Let me add a piece of information about double and triple bonds and bond strength. It doesn't completely apply right now. It will in later lessons when we're starting to talk about how easy it is to break a molecule apart. But since we're learning about double and triple bonds, I'm going to throw this in right now. What happens is, as we add more bond, the bond length decreases. What that means is the distance between the two atoms, or the two atoms, is that as we add more bonds, they get closer and closer together. It also increases the bond strength. So more bonds means they're bonded together more tightly, which I think should make sense. Like if we needed to break this bond, okay, we could break it. But if we needed to break two bonds, that's going to require more energy than it did to break one bond or one of these. And then if we need to break three bonds, well, that's kind of a big deal. Here's the point. If we have a triple bond, those two carbons are held together very, very tightly. It's going to be hard to get them apart when we do some sort of chemical reaction. These ones held together very tightly. Not as tightly as they are over here, but still very tightly because there are two bonds that would have to be broken to break them apart. Over here, this hydrogen, not going to be bonded to that oxygen as tightly as this because there's only one bond holding it together. We've been leaving out one of our steps in Lewis structures. Notice I've just been crossing it off and saying, yes, this doesn't have a resonance structure, but some things do have resonance structure, and we need to know how to deal with them. So the next video, there'll be a link right down there, will take you and teach you how to do resonance structures. Thanks for watching and keep on learning.